Summer in the hills, those hazy days I do remember. We were running still, had the whole world at our feet, watching seasons change. Our roads were lined with adventure, mountains in the way couldn't keep us from the sea. Here we stand, open arms. This is home where we are, ever strong in the world that we made. I still hear you in the breeze, see your shadows in the trees, holding on, memories never change.
Yes, you will not be able to hear myself because, well, because I actually turned, muted the microphone. But it should be fine now, so hello everyone, please let me know if the audio works now. And I guess we can get going with today's today's live stream. Yes, I can hear myself on YouTube, which probably means you can hear me as well. So, officially now, hello everyone, and good evening, welcome to another of my live streams. Today's moderator is going to be, I think, Foxtrot Charlie. His nickname is right here. And at the beginning, you might see KrzaQ as well. So if you have any questions at any time, then do tell them to pass them on to Foxtrot Charlie. Because Foxtrot Charlie, his nickname is again here, will be able to pass me the questions on our magical portal, which is related to unicorns and stuff. And yeah, that's how we actually pass messages around here using unicorns. Anyway, but before we do that, I actually need to open our magical portal as well to be able to read the questions from you folks. Here we go. Okay, that's perfect. Now, today's topic is kinda random, and I'm not sure how long will it take. Probably not so long, but we'll see. Anyway, the topic is going to be benchmarking, and because benchmarking on one hand seems like a trivial thing to do, and there are actually several gotchas there which catch especially beginner programmers off guard. And also, I guess, even if you're not a beginner programmer, even if you're a senior programmer, and if you do not do benchmarking a lot, you might fall into some traps as well. Though, on the other hand, you probably know how complicated it is to get everything right. And you probably also know that it might not be fully possible to get everything right in the end anyway, but that's fine, and it's still, we can still achieve whatever goals we have. So, before we get there, let's do a set of usual announcements, and I guess I will start in a couple of minutes. I will probably not do a lot of questions from you folks today. At the beginning, I will do them during the live stream. Just, since the start of the stream has already been delayed a little to not drag things even further. So let's go to the usual stuff. And yes, this is Foxtrot's blog. So visit it. It's foxtrotlabs.cc, and again, thank you to Foxtrot for helping me out. And we are going to see if Foxtrot has written finally a post for us, and almost, yeah. So do encourage Foxtrot to actually write blog posts, and do encourage KrzaQ as well if he's actually watching, or if he's on chat. I think he is on chat, so we can encourage both of them at the same time. It's like hitting two bloggers with one request. Okay, then I guess the news of the week, and something which you might have heard before on my live streams, is yes, paged out website at least is up, and the official call for paper is up as well. So I have been, well, I've been, oh wait, I'm actually going to pass you the link on both our chats, or actually all three of them, because we have YouTube chat, we have IRC, and we have Discord. Anyway, so Paged Out is a new project which I had in mind for several months now, but I finally got to officially start it. The project is basically a free internet magazine, as in a PDF format, with let's say about everything which I care personally about, everything technical, like deeply technical I personally care about, which would be programming, especially programming tricks, hacking, then security hacking, retro computers, modern computers as well, and modern technologies, electronics, like even amateur radio, which I have somewhere on my to-do list to learn, demo scene, and other similar stuff. So like I'm basically trying to create a new magazine for folks who are into the, you know, like the deeply technical, low-level stuff. Not only low-level, but I guess like due to the nature of the topics, that kind of goes that way. Now, here's the trick. Actually, each article in Paged Out magazine is going to be only one page. That's why it's called Paged Out, because, you know, each article is on one page. Yeah. Additionally, the author has full control of the layout. That actually means also the author has to actually make the layout of a page, but it means the author has full control of the layout, so it doesn't have to be, you know, a standard 2-column set. It can be anything. And I guess I can show you the example article written by KrzaQ, Q3K, and it looks like this. You can actually find it on the website already. Yeah, it's basically one page. It's about this device which turned out to be a cheap FPGA, and there's some example code to it, some additional interesting stuff about it, and everything fits nicely into one page. So that's basically the idea. Like, one page is, the idea is it's easier to write because it doesn't take as long to write one-page article as it does, for example, 10-page article and polishing it up. And on the other hand, it also takes less to read one-page article. And if you're writing a one-page article, you are not, you can focus on the little stuff, right? If, for example, you would be contracted to write an article to some paper, a technical paper, you usually think about big things, like full tutorials about everything, or like whole projects to be described. But if you have only one page, well, you can write about one simple trick which you learned, which is really funny, which is really interesting and entertaining, and that's fine, because you can easily fill one page with it, and you will not feel guilty for not writing 10 pages about it, because you have only one page. So that's the idea. Basically, it's not to, you know, be like supersede FRAC or like POC or GTFO. Is like totally different category of articles, just like one-page articles. So that's the general idea. And we hope the first issue to have at least 50 articles like that. So yeah, we are currently looking for authors. So if you're interested, go to pagedout.institute and check the call for papers page. There is no deadline, but I think we are going to get around 50 articles around a month from now. And then we'll start to put everything together, and hopefully the first issue will be around June, July, something like that. And yeah, I guess I showed you already the probable first art for the cover art. If not, then here we go again. Yeah, we basically, well, as you can see, the colors might be similar to my layout, but might be related to the fact that it's actually my project. Anyway, we actually asked several artists to do some fancy drawings, which are in the blue to violet range of colors, and they have something similar, something in common with like the themes of sci-fi or cyberpunk or hacking or whatever computers. And this is the first one we got, so it's probably going to be the cover of the first issue once we get to setting it up. So think about if you have something to write about, like, you know, just one page. It can be a cool programming trick, it could be a small electronic project, it could be a write-up for a CTF challenge which fits one page, it could be anything. Actually if you go to the call for pages and then to writing articles, it's, I think the first, that doesn't, that works. Okay, so here are some example topics, and these are just example topics, but look at them, think if you have something in mind, and think if you could write an article for us. Especially that, you know, first issue is always the most magical, so if you make it by, I guess, in the next couple of weeks, then it should make it to the first issue. If you're not interested in writing an article, but you're interested in helping out our project anyway, then do look in the How Can I Help page. There are some things which are super important, which are not related to writing articles, so do take a look. There's things like making templates, like just asking your friends if they would, like, if they make awesome stuff, right? If they would be interested in making an article, or even like at some point we will be, when we have articles, you will be able to record some articles as podcasts to basically enable folks to listen to it without having to read it. And yeah, so do take a look, and I guess this is what I spent the last weekend on. I'd also like to do a shout out to the current team, which I call the Paged Out Institute. This would be Foxtrot Charlie, which is acting as like somewhat between a project manager, I guess, and an assistant for me. Then Yuru and KrzaQ are the first reviewers, technical reviewers, who will make sure that all the articles are as polished as possible when they reach the audience. We might be looking for more editors later on, especially after we know how the process works, because we want to make sure that everything in the process runs smoothly at the beginning. So yeah, and also like there were other folks who, for example, created the logo for us, or okay, why does it stop working? That's pretty weird. Oh, my keyboard just froze. That's perfect. I guess I will have to restart it in a second. Anyway, there are also other folks, like for example KrzaQ, who written the first article to test the whole idea. And yeah, it actually took him like 30 minutes. I threw the idea on our IRC, and like half an hour later he comes and says like, here's your article. And I'm like, wow, this is just amazing. Yeah, also the artists who made the cover and so on. So thank you for helping out, and let's hope to make this a successful project, basically. I guess this is the biggest news I have. So yeah, the call for paper is officially opened now, and there's a lot of information on the website. If you go to like FAQ, I tried to write some stuff there. For example, why is there a one-page limit, and why does the author needs to prepare the layout, and what is our business model? There's basically none. This is kind of a non-profit project, but we do hope to make it self-sustainable at some point. Hopefully, let's see how it goes. So yeah, look, my keyboard just unfroze. Okay, that works now, zooming works now, that's perfect. So there's that. If you have any questions, then do let me know. I think there are a couple of questions, so only 3 questions, so let's do them quickly. The questions will appear here. So, when will we see new missions? I guess as soon as I'm catch up with a backlog of missions, then it might be a while, in all honesty. It might be still a couple of months before I figure a way for the missions to be, for everyone who solves the mission to be properly credited, and at the same time for it not to take me too much time of my schedule, since I always have to, like, balance my schedule, which is sorry. Am I using LaTeX? No, not really. I mean, again, because the author is actually responsible for writing the articles and for laying out the articles, what we get at the end is a PDF. So whatever the author uses for the article, that's fine. It can be LaTeX, it can be Inkscape, for example, was what Q3K used. I might use Google Docs or like some even presentation tool or whatever. That doesn't really matter, as long as at the end you get a PDF which has the proper dimensions, that works. And yeah, we hope to get some templates for various technologies and various like applications for Inkscape, for example, or for like Word or whatever you want to use, for at least the basic layouts at some point. But yeah, in all honesty, I hope for some donations of templates from folks who might be able to help us with that. Are there any topic restrictions? Do look at the writing articles page. Everything is explained there, including what we will probably not publish. Like basically non-technical stuff. We might publish some non-technical stuff from now and then, but we will focus on deeply technical stuff. And there's also somewhat similar to a 90-day policy for 0 days. But yeah, take a look. It's a great question, Matthias. Cool. So let's chat about today's. No, the issues is like the issues will be typical magazine. So you get a PDF which has 50 pages, and each page being one article, one technical article. And yeah, that will be an issue, basically. So you can, go ahead and read. That's basically it. It's a magazine, or rather a zine, I would say. Like that's what we usually call them in the biz. Yeah. Sweet. So let's, I guess, switch to today's topic now, which again is going to be benchmarking. So I will do some hand waving and then we'll do some experiments, I guess. So let's start with hand waving. As in, basically the idea behind benchmarking, right, is to measure how long something takes. Like, for example, you've created this new program or like implemented this new algorithm which does something, and you want to compare it with your previous algorithm and actually check, hey, is it faster when it does this or is it faster when it does that, right? Because algorithms and like data structures have this like thing to them that they are good in some spaces and they usually lack in other spaces. For example, a linked list is great for adding stuff. Like, it's super fast to add something to a linked list. Now, seeking something in a linked list which matches a certain pattern or like has some other criteria, right? That is horrible. That is really slow. On the other hand, you have like, for example, trees, right? Or like hash tables, where adding something is a little bit more complicated. It's not super long, it's not super slow, but it is more work actually to do than a linked list. And but then like seeking for something which meets the criteria, especially if the criteria is actually related to how the data structure works, that's actually usually really fast in comparison to a linked list. So if you want to basically check how long something takes, well, you need to benchmark it, right? And then if you're benchmarking the old thing, then you can decide that, hey, it's actually better or it's actually worse. And it sounds really easy, just measure the time, right? It turns out there are a couple of problems with it. So these problems are what I'm going to talk about. But let's start from the beginning. What you usually want to measure is time, as in how long did the execution take. And the usual mistake that folks do is, for really fast operations, they tend to measure the time of just one operation. And this rarely works. And this doesn't work because we first need to ask a question of, from where does the computer get the time? how does the computer know how long something took, and like what time actually elapsed from like this point, or like rather this point to this point, right? So yeah, let's talk about it. From where does the computer take the time, and what kind of timers do we actually have that we can use? Okay, so my keyboard frozen again. Let's just kill my. I actually written something like lfix. Lfix means kill the Logitech drivers and restart it. Yeah. Okay, I think it didn't restart it. Okay, seems it's actually frozen for good. No, I did kill it. Okay, perfect. Did restart it though? Okay. Might be issues with my keyboard actually. But that's really important for me to zoom today. Oh my, oh my. You know what, I think I'm going to reboot my keyboard. And to reboot my keyboard I have to figure out which USB it is. And so give me a second. Okay, here we go. So my keyboard is, I think, rebooting, and yes, it rebooted, and it works, perfect. Now my keyboard is actually, it has like these rows of additional buttons, and I have macros on these buttons, for example, for zooming and drawing. That's why it's so crucial for me to actually be able to do it. Perfect. So we are talking about the timers. What kind of timers do we have in a computer? And there are actually a couple of them. And when you're talking about timers, you need to think about two things. Well, I guess like on the timer level, on the hardware level, it's only one thing, and that's like, what's the interval of the timer? How frequently is the timer incremented? Because that tells you about the resolution of the timer. And when using APIs, because these hardware timers are then, used by the operating system kernel, and the kernel has some APIs, and then when you have libraries on the user side, on the user mode, these libraries do kind of like use various kernel APIs as well. And in the end, what you get from the libraries is some unit of measurement, and the units can be, seconds, milliseconds, microseconds, or nanoseconds. I don't think we are going below nanoseconds at this time. What's below? I think picoseconds. Please correct me if I'm wrong. So yeah, what we have and I'm going to talk only about x86 because this is really hardware specific. So if you are using a different hardware, not a typical x86 on a normal motherboard, then you might have different timers. Sorry, I'm pretty sure you will have different timers. So yeah, the first one is PIT, which is stands for like programmable interval, I think, interval timer. And it basically works like this. And we will have to check that, but what's the exact frequency? But every some period of time, which is rather short, it basically interrupts the CPU. It like tells the CPU, hey, I just incremented my timer, and like do something. Now you can actually program if you want to do that for every tick of the timer, or whether you want to do it every several ticks. And the PIT has one frequency basically, which is it operates on, and it's not a high frequency. So let's actually take a look on Wikipedia for that, because I do not remember this out of programmable interval timer at the top of my head. Here we go. And yeah, this is the clock, which means it basically is like 1.2 megahertz, which is the frequency of it, and which means it basically does a tick every you can program it to signal you every one by like 1.2 million of a second, or less frequently than that. That's actually what, like, whatever you put here is called a you can program it to have a divider, so it actually interrupts the CPU less frequently by some factor. Anyway, so that's one timer, and as you can see, the resolution here it looks pretty good, right? But in the end, the system timers might actually program it to be interrupt the CPU one by 100 of a second, 100,000 of a second, so only 100,000 times per second. And so this is one timer, and what happens basically is that the CPU, like actually the kernel, has some variable. Let's call the variable, like, I don't know, like timer, right? And this is basically an integer which is incremented every time the CPU gets a tick. So I don't know, if the CPU, let's assume this variable at the start of our operating system is actually 0, then every time an interrupt is done, this variable is being incremented. Now, just having this variable doesn't really translate into seconds, milliseconds, or microseconds, or nanoseconds, right? So what the kernel does is the kernel basically knows the frequency of how frequently this timer is being interrupting the CPU, and the variable is being increased. And knowing how frequently this is happening, the kernel can translate actually this variable, right, the timer variable, into which is again expressed in tick counts, which is, the tick counts are again something which depends strictly on the frequency of the timer, and the kernel can translate these to whatever number of, like, let's say, milliseconds it is. Now, so this is one thing, and as you saw, for example, right, the frequency of that PIT timer is about 19 megahertz. And as you know, current CPUs are operating at around, let's say, I don't know, I have something like 3.5 gigahertz here, which means that I can do like a CPU, even if the timer, and I'm not saying it is, but even if the timer would issue an interrupt with every tick, and I don't think that's what's happening. I think it's issuing a tick every like 1,000 cycles or whatever, right? 1,000 ticks. But even if it would issue an interrupt and tick the variable, like increase the variable with every timer tick, it would still mean that around 300 instructions, like CPU instructions, or actually CPU cycles, manage to take place between ticks. So if we would use this timer for benchmarking, and you do that usually by, querying what is the value of the timer at the beginning, then running the operation, and then querying the timer again at the end, and just checking how much time did elapse between these two timers. What's the difference between these two timers, right? And if our operation, whatever it is, we are benchmarking, would take less than this amount of CPU cycles, then we would just get a result of 0. And this isn't really telling for benchmarking, right? Like, 0 doesn't tell us anything. Does it mean that it was instantaneous, or does it mean that it took whatever is below the actual resolution of the timer? So the PIT timer might not be enough to measure things, and I'm actually going to discuss now what timers are better for that. And at the end, I'm going to tell you it doesn't really matter, because this timer is good as well, but you need to change the approach of how we do benchmarking. So, okay, we already have PIT, right? Which is, again, the programmable interval timer. This is the old thing. Then the x86 got something which is called HPET. This stands for high precision. Apologies for the typo. Event timer. And this is something which appeared in the 2000s, late 2000, something like around Windows XP, basically. And it's basically a similar thing to PET, but it's actually way faster and can take way faster. So let's, I guess we can check on Wikipedia how fast the HPAT is. What's the frequency of it? And 2005. So that was like around Windows XP, actually a couple of years after that. But I do remember that XP had support for HPAT already. And like frequency or something, can we? Yeah, at least 10 megahertz. So it's it can be more, it can be less, but it's at least 10 megahertz. So that's already gives us a better resolution than whatever the PIT could give us in the past. And yeah, I guess it also has like memory mapped I/O, which to me translates that perhaps it doesn't even have to issue an interrupt. I'm not sure how it exactly works, but perhaps there is just some memory value which the CPU can read and know how many ticks did actually elapse. Then if we actually go the other way around on the timers which have less precision, then we have the RTC, which is the real-time clock, which measures, seconds basically, and perhaps milliseconds. Seconds, or like, I'm not sure about which one. Is it milliseconds or is it seconds? But this is what basically keeps the real time of the world. It was, I guess, more important in the past when you basically had only the BIOS time to know what the real time. This is basically the BIOS time, right? To know what is the time in the real world. And currently, I guess operating systems can use whatever timer and synchronize the time with a time server using some time-specific protocols to make sure that the time is properly set and really accurate, and then just use whatever timer to increment it. But yeah, just to mention that also the real-time clock is there if you need to query it for like second level precision, and if you're writing an operating system, you might actually encounter it. And the last thing, which I guess is somewhat most important, and I did see already that on chat you did jump to it, is something called the TSC, which is the timestamp counter. Stamp counter, and that's actually a nice name for CPU cycle counter. Basically, the CPU has this register TSC, which is incremented with every CPU cycle, and this is the best resolution you can possibly get. There are some issues with it, but this is the best resolution because it's related to your actual CPU speed. And as I did mention, like CPUs currently are around like anything from like 3.5 G. Well, actually, like if I'm saying from, I should say actually, wait, this works weird. From like 2 gigahertz to let's say like 5 gigahertz, right? Unless you overclock even harder. And this is the resolution you get. Every like half a nanosecond or 0.2 of nanosecond, you actually get an increase of a counter which holds the timestamp. And it's basically guaranteed on a CPU that nothing will happen between the cycles. So every operation needs to in the end fall into the, into the cycle buckets, like it's either happen in this cycle or in another cycle. So that's why you do not need more precision to measure something than a timestamp counter. Now, there are a couple of problems with that. Let's start with how do you translate CPU cycles into seconds. For example, I want a result in seconds or a fraction of a second, right? And I have a CPU cycle counter. How does that translate? Well, the obvious answer would be to, hey, if you know your CPU is like 3.5 gigahertz, then why don't you just like take whatever the result is, right, and then divide it by 3.5 times 10 to the power of 9, because that's actually what gigahertz are. And yeah, that would work in there was a period in time where that would actually work. Now, the problem is something called like variable frequency, basically, of CPUs, which means that the CPU frequency can be changed by the operating system. It can be either lowered to, for example, save power, or it can go higher. So for example, if you have a a mobile phone, right, these things tend to go down with the frequency if possible, because that saves battery time. And then if you start playing with the phone, then it actually boosts the CPU to the maximal power to make it more user friendly, more usable, more well, I guess fluid. The interface is more fluid and the animations work and everything. So you do have to take into account that, as in how much of that time which you measured was actually under lower frequency, how much was under higher. And if you have a somewhat modern x86 CPU, then usually there's something called turbo for the cores, and depending on the CPU model you have, one or more cores can go into turbo mode and get even more frequency on it, like be automatically upscaled to be faster. And then your application might actually, like the process that you're measuring, your application might be scheduled to a normal core which is running under normal frequency, and then it can go into, for example, this turbo core which is running with turbo frequency, and then again to a slow core, and so on. And then, for example, the operating system might say, let's actually scale down the turbo core because we no longer need it, because the CPU doesn't need to do so many calculations right now. And because of the scaling, actually converting the number of cycles into a normal wall time is kinda hard, but the operating systems usually provide you a way to do it, or do it themselves. So there are timers provided by the operating systems which operate on, for example, on nanoseconds. And this actually in the background operate on the timestamp counter, but the operating system makes sure to do the conversions as they go, and the operating system obviously knows when the CPU is being downscaled or upscaled with regards to frequency. So yeah, again, we are chatting about benchmarking today, if you're late to the live stream, and I'm basically going through the theory of why it's hard why there are some problems. If you know how to do it, it's easy, but usually there are some problems which people fall into. And yeah, there was a chat on our Discord about it, so that's why I thought I'd make an episode about it. So yeah, so ideally you want to use anything which is related to the timestamp counter, but as I mentioned, there's actually one more thing which must be mentioned here. In an ideal world, when you would read the timestamp counter, it would actually give you the result of how many cycles did actually pass from. Well, no, it will give you the current value, whatever the current value is, like the value from when the instruction was executed. But because our CPUs currently are heavily pipelined, they're super scalar, they're using like out of order execution, speculative execution, and some other ideas, then this timestamp counter is actually a little bit more tricky. And there's this assembly instruction which is called like RDTSC, which is read timestamp counter, which basically gives you a 64-bit value. Originally it was 64-bit value which was put into two registers, which is AEX, ADX. I think the higher bits were in the ADX. I would have to check if on 64 bits it's still like that, or if they change this to just like one register. We can check that in a second. So if you would do, for example, RDTSC, and then like, I don't know, let's say you would move the registers, because you need to preserve the values, right? So you want to move like to EDI, put EAX, to ESI, put EDX, and then do whatever operation. For example, let's say I want to check how long does it take to push this value on the stack, right? And then we do RDTSC again, read timestamp counter, yeah, and then you basically do a subtraction between, subtract the old value from the new value, and you get how long did it take, and you might arrive at something like 0, for example, because the way the CPU decided to execute these instructions was to execute this first, but in the meantime execute this already. And then this is already executed or scheduled for execution, and the CPU knows that we don't need the value on the stack later on, so it can just happily move to executing this instruction and whatever instructions are here later on. So this might be executed out of bounds, basically, right? Out of order. It might be executed out of order. And then you might get like 0 because of different reasons, because the instructions both were in the pipeline and blah, blah, blah. The current CPUs are super complicated, so being able to benchmark one instruction of assembly is basically super hard, tricky, and basically not happening. So, yeah, given this, you actually have to take care around using this instruction, and you might want to serialize the execution. So the way it was usually done in the past, you'd call, before calling read timestamp, you'd call like CPU ID. CPU ID actually puts some CPU related information into some registers, but that doesn't really matter. What it also does, it basically acts like a fence. It makes sure that all the instructions are executed before the CPU ID instruction finishes, which is a nice way to make sure no out of order and like parallel superscalar execution is going to happen. So yeah, you do this, you do CPU ID, then you do RDTSC, and then you do whatever, and then you do again CPU ID, and then you do RDTSC, and you keep your fingers crossed that that actually worked. So yeah, doing single measurements of really small instructions is tricky. Furthermore, it's not really that useful, because if you would like, for example, if we would have an algorithm, right, and you would take each instruction from that algorithm, you would measure that one instruction, how long does it take to execute, and you would add the time of the execution of all these instructions, you would probably not arrive at the correct result anyway. Because first of all, again, because of all these CPU optimizations, which I did mention already, so because of superscalar, out of order execution, and so on, your algorithm might just execute faster, because some instructions would be executed in parallel, or some instructions might be executed while the CPU is waiting for some data. And this is actually great, because it means the algorithm will run faster, but it also means that we will not get the same result if we would just measure every instruction separately. Furthermore, as soon as you start touching memory, then your results will vary depending on whether that memory is already in the cache. Is it in cache level 1, level 2, level 3? Or is it in RAM and has to be fetched, for example, or has to be stored in the RAM, but that usually doesn't block anything or too much. Anyway, and if you, for example, run your one algorithm and for some reason all the information was in cache, it might turn out that everything was great. But then if you run another algorithm and all the information was in RAM because of reasons, it might turn out that that algorithm is slower, which might not be true if you would run them both at the ideal conditions of everything being in the cache, assuming that both algorithms would be obviously capable of behaving like that, right? Because there might be some problems with algorithms versus caching, but let's not go over yet. And another thing is, when benchmarking, you also need to take into account what is the rest of the operating system doing? Because if, in ideal world, the thing which you are benchmarking should be the only thing running in the operating system. There should be like no services in the background, no applications in the foreground, nothing. Only that one thing which you are benchmarking. And actually there should be like as little hardware which might generate an interrupt as possible. Because when you're measuring time, there might be several things which might happen, right? For example, an interrupt may come, like some network data has been sent and the CPU needs to process it now, and whatever you're measuring will be interrupted. And we'll get to measuring stuff without taking that into account later. So that's one thing. The other thing is, if you're running on a hyper-threading CPU, you know, a CPU which has cores, which then the cores are split into 2 or more logical processors. Sorry. Then if another thread which is on the other logical processor on your core actually takes some execution modules out of, like, just occupies these execution modules, then obviously your logical thread will not be able to use the same CPU modules and like execution modules, and therefore it will not be able to execute on them, and that might also add some variations to how much time did you measure. And then there are like logs in the kernel. If you interact with the environment, for example, you want to read a file, and basically the file system is logged every time any thread requests some file, and the file needs to be looked up in the file system, or like whatever other operation on the file system is being made. So if you're measuring a thread which does something on the file system, and then you have like some background processes doing backups, for example, then your time will be way longer, even without, you know, thinking about stuff like the physical head of a physical hard drive having to like just run around doing some work for this process and some work for that process, some work for this process. It takes physical time, you know, for the head to move. So even not taking that into account, therefore, if you're doing benchmarks, what you should do is you should have like close all the applications, because and try not to move your mouse, because when you're moving your mouse, that means that you are basically issuing interrupts. Well, that was true for, I guess, the older mouse, but the current mouses are a little different, but whatever. Yeah, in the end, you might issue interrupts, and that would mean, well, you are actually making the process slower just by moving your mouse. There are some stories that I've heard, I guess, from chats with folks from OSDev, like the IRC channel on Freenode, that there was a case of a computer which had the timers dead, basically, but which means that the operating system, you know, would just freeze. But if you move your mouse, that would actually send interrupts, and interrupts would allow the scheduler to switch between tasks. So if you would move your mouse, then the operating system would keep working and worked correctly, but as soon as you stop moving your mouse, then yeah, the system was dead again. So that's basically what happens if you don't have any timers which would allow the scheduler to jump in, take the CPU from one thread and switch it to another. Anyway, just a side story for you. Okay, so we know that. Now, how to actually do more proper measurements, and I guess there are a lot of ideas how to do that. What I would personally suggest to do is to not measure one operation, measure 1 million times that operation. So for example, if you're measuring how fast do you seek something in a list, measure 1 million times, and actually measure, you know, start the timer, then do the 1 million operations and end the timer. And then you can actually, well, take the result. You can, if you wish, you can divide it by 1 million and you get the average of how long on average did that take. Furthermore, actually, when you do that, do this million operations, do it, for example, 100 times. And then when you do it 100 times, take the minimal result, because the minimal result will actually be the result which had the least interference from the outside world and had the best cache, probably the best cache, well, usage there, or best RAM usage. And yeah, that's the result which is as close to a usable result which you can have. And yeah, and it won't be perfect. It will still not be the perfect run or execution of that environment in the world of perfectly spherical chickens, or whatever other perfect world would you like to discuss, right? It's still going to be somewhat influenced by the operating system and the outside world, because we just cannot get away from that. But if you do enough iterations, like 1 million, for example, the differences between running two algorithms which you want to compare on the same computer in the same settings will be meaningful, and you can make a decision whether one is faster in a given operation or whether one is slower in a given operation. So that's basically the gist of it. Now there is one more catch, and that catch is related especially to stuff like Java, stuff like C++ and C. And that's actually optimization. As in, our compilers have gotten so good that if you do an operation just to do that operation and never use the result, the compiler will just say, this is dead code, I'm going to remove it. And you will end up measuring nothing, like measuring just space between two timers run one after the other, and you will get funny results. So what you need to do is you need to make sure that there is some side effect which tells the compiler the result is actually being used. Do not discard the code which does this. And that's super important, and you can, I guess, fall into the trap even without using optimizations. But I guess, like, if you're not using any optimizations and if you explicitly disable any optimizations related to dead code elimination, then it should be fine. But on the other hand, just to be sure, and you, in all honesty, you usually want to run algorithms with optimization, because that's how you run on production. You run with all optimizations enabled, right? Or at least good quality code, you can do that. And so you need to hook up the effects of that code to something which is after the timers, which actually uses it, so that it's not being optimized away by a compiler. Yep, so that's basically the theory behind it. Now we can do some experience and play a little with it, and I'll try to make all the mistakes which I did tell you about, or at least some of them, and we can take a look how that works. Now, one more page I actually wanted to show you. It hasn't been updated for a while, but if you go to my notes, like Gunveil Colvin PL/n, then there's something like resolution and update intervals of different time fetching functions. And if you go here, you can read about the timestamp. Oh, there's also the local uppeak timer, which I did not mention. Well, whatever. There's another timer. Yeah. What you will see here is basically the function names and the environment, and also how frequently they are updated, and what's the unit of what they are returning. Is it milliseconds? Is it, I don't know, nanoseconds? Is it seconds or whatever? For example, if you see time, right? Time is here. You know that it's number of seconds. So you get the seconds in case of this function, at least in C. In Python, you get also like up to microseconds, I think. But so that means that this timer, which is used by time, is basically, we can say that it's updated every 1000 milliseconds, because that's what makes a second. So, which means the actual resolution of a timer is 1 second. And this is important when you start to look at stuff like this clock from Debian, where the clock and this is an old clock, by the way. I think they already changed it, which is a good thing. Now, they say that the function returns this unit, which is basically, let me count the zeros, microseconds, right? So it returns how many microseconds did elapse from some event. And that would be great. That means that, hey, we have a timer which has microsecond precision. That's great. And not true, because it turns out that the timer which this function was using at the bottom actually was updated every 10 milliseconds. So the timer, the counter, actually was updated by this number of units every 10 milliseconds. So actually what you get is timer which says it returns microseconds, but actually it's being updated every 10 milliseconds, so the precision is actually 10 milliseconds. So there's that, and you do have to, when using a timer, you basically have to remember to know what kind of measurement are you getting, because even if the unit is milliseconds, it doesn't guarantee that, or like nanoseconds, it doesn't guarantee that the update of the timer counter is actually done in the same unit. It can be done with like again, for example, like 10 times slower than the counter would suggest, like, sorry, what the unit would suggest. Okay, so let me take a take a quick look on the questions. Will you also include show questions? There are only 3 questions, so this will be fast. Will you also include constant time in the stream? So yeah, I guess there is. I guess I should also talk about let's say algorithmical complexity in versus the wall time benchmarking, because it's like this: when you're discussing something with somebody who does algorithms, or if you're actually in this mindset of doing algorithms, you usually think about the capital O notation, which means, for example, if we go here again, if you want to add something to a linked list, that means that it's O of one operation, which means it's actually the operation will take, regardless of how much data there is on the list, it will take 1 unit of time, and this 1 is actually like a constant number of operations. So regardless of how long the list is, it will always take a constant number of operations. It doesn't have to be like 1 operation, it takes like whatever number of operations, right? If you search through a linked list where you have to there is, like, for example, n elements in the linked list, then you have to visit every element to make sure that is not the element you are looking for. So the worst case scenario would be O of n. You have to do n operations to visit every element of a linked list. Even if you would have to visit it twice and it would be actually like, I don't know, like 2 times n, you usually just say O of n. You totally ignore the constants, and that's how it works. And I mentioned the trees, adding something or looking for something in a tree at the beginning, and usually what you would say is that it's actually log of n. That's the complexity of it, because it means if you have 1000 elements in the tree, in a binary tree, for example, that means if it's a perfectly balanced binary tree with 1000 elements, it means it has 10 levels. And the logarithm of 1000 with the base 2 is actually 10. So that would mean you have to do 10 operations to find something in the worst case scenario, which is actually the correct answer here. So this is the algorithmical complexity, and for large numbers, for large n's, it's actually what you should be caring about when optimizing stuff. Now, if your n's are actually lower, then the implementation speed matters a little more. And lower, I mean like really small. Then the implementation matters. And if you have like 2 algorithms which has the same big O complexity, then it is all about the implementation. And there are, like, if in algorithms we would say we have an algorithm which has actually O of 1, which is the constant time. It always takes the same amount of time. It still boils down to the actual implementation of how long will it actually take. And there's also like some stuff, like, for example, if you have a properly done hash table, then you would say that fetching something from that hash table is an O of 1 operation. It's like a constant time operation, which isn't actually true from where I sit, from the security point of view, because there were some, and it's quite obvious. If you know the hashing function for that hash table, you can actually make it collide and make it go into a worst case scenario where it turns into, like, let's say, a linked list complexity of O of n, and or even worse in some cases. And there was a couple of years ago a series of DOS style vulnerabilities on stuff like Apache, PHP, Java, and so on. Exactly in like implementation of hash tables, which are on paper should be like O of 1, but actually it turned into a DOS because it's not really constant time. But that's like somewhat of a digression. If you're doing benchmarking, you're actually measuring the implementation time, right? And you have to take that into account. And you should know what is your algorithmical complexity of that. I know that algorithmical complexity scares some people, but this is actually, like, I always find this concept trivial. So yeah, don't be scared of it, like just learn how it works. There isn't a lot of theory behind it, even if the formulas look scary. If you start like, if you get like grasp the idea behind them, they're like, this is a kind of a trivial concept. Okay, and I got a link to something from KrzaQ, let's see. Oh, that's actually a really great link. KrzaQ, if you could, or I'm actually going to give you the link to benchmarking and C++ from CPPCon, which actually looks really amazing. I'm pretty sure, I didn't watch it, but I'm pretty sure I have it on my to-watch list to watch it at some point. So do check out this this video. I guess I can show you it here as well. Here we go. So yeah, check it out. I'm pretty sure this is an ultra interesting talk, especially if KrzaQ recommends it. What about performance counters? Yeah, I did already talk about performance counters, so I guess we can skip that question. Perfect. Now let's do some benchmarking and let's do some mistakes in benchmarking as well. First, we're going to do some Python because Python actually has a benchmark module. Sorry, I need to create a directory for this. Oh, I'm actually going to tell you one fun story. I recently was doing slides for some conference and I was using Clock to do benchmarking on a Debian, which is somewhat not updated. It turned out that the timer was not being... No, it's actually the timer worked correctly, the timer which works in the background for that clock command, but for some reason the clock command actually always returns 0. And it took me a while before I realized that, hey, it's actually the C library which is misbehaving. So it's rare, but that happens. So make sure that your timing functions actually work. And if you're looking at the like subtraction of like before and after measurement of the time, then you get 0 and you're like, this operation maybe is like just too fast and I need to like make 1 million of it. But if like something like 1 million operations, which actually I saw it took more than 10 seconds and it still gave me 0, I became suspicious of the timer and it turned out that the timer was always returning 0. I don't know why. I didn't in the end look. I tried like debugging it a little and looking into the Debian glibc repository for whether there were bugs like that, but in the end I decided I just need to do the slides for the conference first before I do the fun stuff of trying to debug this. Okay, so the Python has, as I did mention, Python benchmark. Yeah. What's oh, perf, that's probably it. Or is it? I don't remember what's the name. We actually need, sorry, I need to make the font bigger in my console. Give me a second. Time it, thank you. Who cares? You're amazing. That's exactly the name I was looking for. I always forget. Okay, here we go. Perfect. So, time it. As I was saying, it's called time it. You can actually run it from as a command line tool as well. And it has this like, yeah, time it method. Whatever, help. Time it. I don't even know why did it actually run a system command on me. But whatever. Yeah. You basically give it a statement and you give it a which you want to measure. You give it a setup function, which this is basically Python code in both cases, and it can use some timer which you specify or the default one, and how many times do you want it to execute. So this is a pretty normal thing to run like a million or so operations. So we can actually try to time. Let's do something like this. Let's assume we want to check whether it's faster in Python to add something to What can we do? If you have a list, right? Like this is a list. Then you can add something using append. Or actually, I was thinking about expand. And you can add like these elements. Or you can add something using this. And this is actually the same thing in Python. So let's say we want to check which one is faster. And to do it, we will be using this import timeIt method. Now I think I can actually use it not on the statements, but also on some functions. So import timeIt. Let's see. Yeah, we're using just Python code. Yeah, this is how you use it from a command line. You basically do -m, which is like use the module timeIt, and then you give it the code which you want to execute, and I guess it goes for some amount of loops at the beginning. So, oh, I know what we are going to time. We are going to take a string, and we are going to keep adding letters to it, and we are going to time it against the list and doing append a on the list, and then doing ASDF is equal to ASDF, no sorry, join ASDF. Now, what are the three non-trivial reasons why I'm using Python 2 instead of Python 3? Okay, encode, decode, and bytes instead of Unicode string as default. Here you go. The thing which I said is true for CTF, by the way, and ad hoc tools. It is absolutely not true for production-like code, where I do prefer Python 3. But yeah, for CTF, Python 2 is just better, in my opinion, obviously. As everything on this channel, these are only my opinions. Cool, so let's now try to do it. timeIt. Now, statement is going to be ASDF plus equal A for, yeah, that should be fine. And the setup function is going to be ASDF is a string, an empty string, and yeah, this should be fine. Now let's see what is going to happen, because I do not know this function. We can do it manually in all honesty, but let's try to use a library for a change. It doesn't display anything. Please display something. Okay, it displays the time. I guess it's seconds. So let's tell it times to do it this many times. Unexpected argument. Why is it unexpected? Number. Oh, my bad. Sorry, number. Number. That's not how you spell number. Okay, that takes a long time. Too long. Yeah. Anyway. Now I'm going to add one more. There's actually like a huge difference. This is because the length of the string, I would say. So instead of doing this, what I'm going to do is I'm going to give a different statement to it. Yeah, let's do it like this. I want to do ASDF is a string then for I in X range of 1000. I want to do ASDF plus A, and that's it. Wait, did it work? Yeah, I think it. Okay, now it's way too long. It's probably allocating memory. Okay, now it works. It gives around a second result, which is fine. As you can see, the variations are pretty heavy, and this is because I'm streaming actually, which means there is like my CPU is being used and my GPU as well are being used in the background quite a lot. And my network card is just like spamming with interrupts left, right, and center, because it's actually going to YouTube, right? And I'm getting it back as well. So yeah, this, as you can see, there are a lot of variations, like a really huge difference, around even 20% in the result. Now let's use the other method which I mentioned, which is append if you saw my CTF code, you know I'm actually using the other style usually. Join SDF. Yeah. Yeah. So, and this actually is first mistake I want to tell you about. Now, the mistake is that I'm doing a disservice to this measurement by running it as soon as the application is being started. What I should do is I should run it once and discard the result and then run it again the second time. And this is basically to warm up the cache. Because as soon as like the first couple of measurements are started, then the CPU might not be even trained with how to cache Python properly. And I'm not saying there are like some really hardcore algorithms there, but it kind of boils down to what I said, even if it's a little more trivial. So what I actually should do, what I usually would do, is to like run it once, discard the result, don't print the result, run it then second time and time it, then do the same here. Actually run it twice, discard the first result and run it the second time. The thing that I'm using actually 10,000 iterations helps a lot, and I might not even have to do it. But if I would be using only like a smaller number, then this might matter a lot, just because the cache is not properly, like not everything is in the cache or something. And yeah, let's run it a couple of times. Now the measurement is going for around 4 seconds. Yeah, and it's, I would say, a little more stable now. I guess the variation is a little different. We can see obviously that the second method is actually way better. Now if I would do another thing which we can do is actually change these around and see if that actually changes the results because of reasons. Yeah, what you can observe here is that for some reason when I switched it around, the first, the measurement, which usually was around like 0.7, actually got into the 0.8 territory. So yeah, even switching around the benchmarks the way you do it might influence it. But as you can see, what matters here is that it doesn't matter. But what matters here is that it doesn't matter because it actually boils down to the fact that we see the clear difference. Like the difference doesn't variate enough for us to say that, oh, we might have some doubts that the second method, like the join method, is faster. We don't have any doubts. We know this is a faster method. Yeah, so that's one thing. I don't think like even you do not have to do the empty runs which discard the result. It's not really super important if you have the differences if you are comparing two values and the difference is in this range, then it doesn't really matter either. Now, I actually could do the first measurement because, like the empty measurement, because I know that Python will not optimize it out as that code. This might happen in C++, so let's try to do another benchmark in C++. And try to actually make a mistake there. And I'm going to use the clock from time.h, which is, I think, in milliseconds on Windows. Which is fine. If I'm going to run it for like 1000 times or whatever, that's fine. First, a question: shouldn't a Python string just be a fancy list? So Python string is actually, the problem with Python strings is that it's actually an object which is constant. You cannot change a Python string. Each time you attempt to change a Python string, you actually create a new object. Therefore, adding a's to it means you are creating a lot of string objects, which is kind of slow because you need to copy all the data from the old object to the new object. And yeah, it's for like these sizes, which I was using, like 1000, that's not a lot of copying, but if we would be using 1 million, you'd find out really quickly that the algorithmical complexity is actually horrible for it. It's like n log n or something, or like sorry, it's n square actually. So yeah, ideally don't do that. Okay, there's I guess you want to see some more Python benchmarking. Foxtrot is asking whether we should do benchmark copy versus copy. I guess we can quickly do it since we already have a code ready for Python, so let's quickly do it. I'm actually quite curious as well. So xyz.py, here we go. I'm wondering if there's any difference actually between that. And copy, do I need to include copy, or is that a built-in method? I think I need to include it first, or is it only required for deep copy? So Python, no wait, ASDF copy, or like list copy. Is there, no, yeah, I need to import copy. And there's like copy.copy, which would copy my list. Okay, and there's also a deep copy function, which is sometimes really useful. So let's create a list which will be a range, because a range actually returns a list in Python 2, which is one of the differences between Python 2 and Python 3. And then let's do a copy of it. Let's even make the list a little bit longer so that copying takes a little bit more time. And I guess we don't have to create this each time, so I'm going to put it in the setup statement to create this list. And in our code, I'm just going to do xyz is ASDF and copy it using this method. This is by the way creating a copy list. Actually, doing anything like this will, this will also create a copy of these elements, which is both a good thing and a bad thing. It's a good thing because it, if you would truncate the list, well, sorry, if you would copy. Okay, because let's digress here for a second. If you want to copy only a subset of a list, let's say I have a list of like this amount of elements, or a string which is this size, right? You can do it in, let's say I want to copy only these elements. You can do it in two ways. The first way is to create a new object of a list which is the proper size and copy all the elements. And this is what, well, I kind of missed, but this is what Python is doing, right? So it's copying all the elements from here, here, and until the end. And then there is another way, which you can be somewhat smart about it, especially if you have objects which you know are constant and cannot be changed, like Python strings. You can create a new object which basically points to this object, but it's a view on this object, and there is associated information that it's actually really interested starting at this offset of this object, and then it's ending at this offset. So you're not copying any data, you just have this view object, which is actually pointing to some other object which exists in memory. Now, this is way faster. You do not have to copy any data, and if your object is constant, you know it will never change any data here. So, you know, if you would actually care about that, then like this being changed something here, it would normally influence the view object as well, but because you know this, your main object is actually constant, it will never happen. So that's fine, right? Now the problem is that, let's say this is 1 gigabyte and the view is actually like 1 kilobyte. So this is 1 kilobyte, this is 1 gigabyte. And if you operate in a way that you get from the network 1 gigabyte packet and you select 1 kilobyte object from it and repeat. If if you'd use this method, you would be, you would get 1 gigabyte of memory, then copy 1 kilobyte out of it, and then free the 1 gigabyte because you discard it. You would no longer need it. The garbage collector could actually, like reuse the memory. But here in this view object method, you cannot really do that because this view method is still referencing the large 1 gigabyte address. Okay, it's referencing only 1 kilobyte, but in the end, you still have to keep the 1 gigabyte object in memory. And therefore, if you would, operate in this like get 1 gigabyte, select 1 K and discard the 1 GB, you'd run out of memory really, really fast that way. So yeah, that's just a digression. Python is actually doing the copying. It's not using a view-like object, it's doing the copying. Both methods can be made to work. You can actually make a mix of the methods, but does sometimes copying and sometimes uses a view object. And if you're running languages like Java or Python, they tend to use tricks sometimes here. Okay, and this is one thing, and I guess I can copy this, and let's do the actually let's do import copy and copy, and let's see if this actually works. I did forget something which is called, I don't know what's it called, semicolon? No, it's not a semicolon, that's a comma. Okay, it's taking some time. Copy is not defined, that's what I was actually kind of worried about, so let's fix it quickly. Okay, import copy. Okay, 4 seconds for, or 5 seconds for the first. And yeah, the difference here is like around, what, 10%, I would say. That's kind of small, I don't trust it, in all honesty. Yeah, you see the variation is pretty large. And actually I was moving my mouse around too, so... And I'm streaming, so... yeah, and for actually these amounts, I would say these methods are equal. Like they are both equally slow or equally fast. We can, I don't want to run it for too much longer, but let's try it one more time, and let's actually do something like this. Let's do a couple of measurements, let's let it run, and I'm not going to touch my mouse, which doesn't matter because I'm speaking. So there is some sound card stuff, there is compression. Yeah, this is like a terrible setup for benchmarking, which I have now running, which is streaming. You do not do benchmarking when streaming because you should not trust the results at all, and I'm not going to trust the results at all. Let's see how we go, however, and I still want to do the C++ example. As you might recall, I did say that what you want to do is you probably want to do, I'm running like 3 tests of each here. What you want to do is you want to run 100 tests of each and select the minimal result, because that's probably the most telling for you. Okay, so in the first case, the second one, yeah, in all cases actually the second method won, the copy method won. But again, I would be careful with interpreting these results like that without making more measurements, and also usually measurements should be explainable in some way, as in you should be able to look at the code and start thinking about how the computer works, how the cache works, how the memory works, and be able to explain why this is faster. It's not obvious usually initially, but if you get the results, and you can usually backtrack to figure out why is one method faster than the other. Okay, so let's do this example, and I'm going to use the clock T. Again, I think it's in milliseconds in Windows, so yeah, this is the normal way you do it. Clock. Again, the timer at the end of the day with enough iterations doesn't really matter. Doesn't really matter. And what I want to display here is the difference between them. So we subtract the ending time and the beginning time. And what are we going to test? Let's test, for example, okay, let's do, I did mention adding stuff to a list, so let's test that. Let's include a list, and let's see how long does it take. So I'm going to create a list here, and it's going to be a list of integers, and it's going to be called LST because my naming is terrible. So LST, and we push back 1. Okay, and I'm doing on purpose the mistake of doing an operation which I know is super fast in comparison to the timer resolution which I'm using. So yeah, do not do it like this. G++ is the FCC. And printer was not declared, but might actually have happened. Okay, here we go. Okay, and we get 0 as expected. Now let's compile with optimizations, and we get 0 as well. So again, let's do this operation for multiple times. Let's do it 10,000 times. I'm not sure this is enough, but let's test it 10,000 times. Okay, we got some result here. I'm not really sure. Okay, I am sure why it's still... as you can see, it actually doesn't exit immediately after printing the number. It still does something, and that something is actually running the destructor of the list, which is, I guess, a side effect which we can count on in case of a list, because if there wouldn't be this side effect, then it might actually be way... might be optimized out. So to compare this list, let's actually do the same with an array. I'm going to create an array, and I'm going to create it in using static keyword. Actually puts it in the data section, which means it puts it in the image memory, basically. Not really heap, but something like heap, right? And not on the stack, which is the important part. And let's call it like array, and let's do it the same. I need to pre-allocate it, which is already cheating because I'm not pre-allocating elements for this list, but I am pre-allocating them for the array. But whatever, this is my benchmark. I can cheat it a little. Actually, you know what? I'm going to do this. Okay, that actually means that the destructor is going to be run way faster than the end of the function. And here, perfect. Okay, and now let's compare what's faster than, is it this array of I is equal, what do we put there? 1 always, okay. So whether adding something to a list or a pre-allocated array is faster, let's see if we can check that. Yeah, we got again 3.5 seconds. That's again, the result is in milliseconds on Windows for clock. And yeah, it's way faster for the array because it takes 0, where for this takes a longer time. So let's actually make this array a little larger so it doesn't take 0. Let's make it, yeah, because this array is way too fast. How is 1 million now? 1 million items. So let's do it for 1 million items. Yeah, again for the list, and for 1 million items of the... It's 0! Perfect! Wow, the arrays are so super fast, right? Now the problem is here that I'm pretty sure that the compiler actually optimized it out. So this is again the mistake which I mentioned, that you need to create some side effect for the compiler to tell the compiler, hey, you know what, I'm actually going to use this result, so it's kinda important for you to not optimize it away. And to do that, we need to just run it on some code, or actually even if we would pass it to some external function, that should be enough. So what are we going to do about it? Let's do... oh, there's actually there isn't a great way to do it in C++, and it always relies on hacks to do it. Even passing it to a volatile function with a volatile argument does not guarantee it. Even if we would sum it, it does not guarantee it. What we can do is we can try to pass it to some external function, and that should throw the compiler off enough. And it's fighting against the compiler. I do not recommend it. So extern, there's going to be a function which does nothing, but the compiler doesn't know that. So now let's just... And it takes actually a pointer to something, yeah. And this should create enough side effect for the compiler, but the compiler doesn't optimize away the array immediately. So something... yeah, the revisor says that what about printing the pointer, for example? And I'm a little afraid that the compiler will say, hey, I can print the pointer without ever doing these calculations. Furthermore, what I could do is I could take all these elements of the array and sum them and print out the result of the sum, right? So touching in a loop each and every element of the array. The problem is that modern compilers tend to take this loop, run it while compiling, and just print out the result. Yeah, they are like the nasty sort. So, sorry, I think that the best way is to, or the ways which I found was to use some, and I am also noticed that KrzaQ is telling about it on the chat, is basically using a volatile assembly, inline assembly, to interact somehow with it, and then then it's actually not being discarded. So that's one way to do it. This is like another way to do it, but this is, I'm actually jumping with a lot of hoops here to do it. And what I also need to do is I need to create obviously this function, and I also need to, it's declared here, now I need to create it. The function will not do anything, but the compiler doesn't know that, and that's enough. So yeah, and the function does nothing. Now we compile them separately just in case. I'm pretty sure there are no linker level optimizations at this point. So I can do -c, I can do, yeah, I'm actually going to leave it like that. And I can compile this -c and then do -o and sth-o and get a as a result. Now let's run it and see. Okay, now the destructors are running, so that still doesn't mean anything. Okay, and we get 1, which doesn't tell us anything again. So let's increase the number here. This is because for arrays, yeah, this isn't really enough of data. So now it's 9 characters. This is currently it's 1 million. It will take like 4 gigabytes of memory. So let's maybe decrease it a little bit. Now I need to compile this. And wait. No, that's good. That's good. And let's see. Yeah, that's a little bit better. And now let's see if I remove this, whether it will still print 0. Actually, like, it seems it's super fast. I'm going to just like use it. Let's hope it does not. No, it should work fine. It should work fine. I'm a little bit wary about overflowing the internal counters for the sizes of how much memory does it have to allocate, like the compiler has to allocate, because I'm operating at near the 4 gigabyte integer boundary, and I'm like for the size of this array. Though on 64-bit compiler, and I have a 64-bit compiler, it should be fine, especially a new one, and I'm pretty sure I have a new one. Okay, let's try to run this. Okay, and I'm still looking for like a higher number, which is... Okay, and now let's try to remove this and let's see what happens. Yeah, let's compile it and let's run it. Sorry, compile it, link it, and now run it. As you know, G++ isn't really a compiler, it's a driver, which means it calls the compiler, calls the preprocessor, and so on. Yeah, it optimizes it away neatly. If we actually generate the code for it, which we can do using -s, capital S, and mass_intel, because I want to see intel, if we look at the generated file, which is called asdf.s, and if we look at the function, and which would be here, then we can look for the second print call, actually. So this is the first print call, and this is the second print call. And where is the clock call? Yeah, if you look at the clock calls, this is what's happening. There should be here, there should be the whole loop, but it was optimized away. So yeah, don't make that mistake. Always hook the side effects or like hook the results of whatever you're benchmarking somewhere. Otherwise, your compiler might optimize it away. Here, again, it's not happening because the destructor of the list is actually being called here, and the destructor does something with the list, and the compiler says like, oh, it looks like it's important, so it will not optimize it away. A smarter compiler might optimize it away as well. So yeah, keep that in mind. And I guess like the last thing to reiterate is, again, think about actually running this code, like a code which benchmarks something 100 times, like put it again in a loop, run it 100 times, and select the minimal result and use that for your comparison. That's probably will be the best number you can use for it. Obviously, I'm saying like 1 million, 100. These constants don't really matter. You probably have to select the constant which matters in or works best in your case. So that's one thing. The other thing which you might be wondering is, how do I use the timestamp counters? And if we go around here on Windows, just use this, like query performance counter, because these tend to use the timestamp counters usually. And yeah, there are usually functions like, for example, query performance frequency, which allow you to know what was the performance of your, like the frequency of your CPU. You can even, for benchmarking, disable the scaling of the CPU frequency and keep it at the same level through whole benchmarking. I think it's a little easier to do on Linux than on Windows. On Linux, I'm pretty sure you can do it like command line with one command. On Windows, I'm pretty sure it's being a little more tricky, and you have to click through some options and maybe even reboot. So that's one thing, but also if you look for like G+ or GCC RDTSC, you will find a lot of code, especially on like Stack Overflow, which allows you to just like get a function which returns a 64-bit integer, where, as you can see, they do use the CPU ID for serializing, which I did mention, and they call the RDTSC and return something. But this is for Visual Studio. For GCC, yeah, here it is. And it doesn't use the CPU ID anymore. I'm actually not sure if the CPU ID is still needed on modern CPUs. I guess I would defer you to Intel manuals to double check it. I know it was quite useful on previous CPUs. And yeah, I guess that's it for today. Let's see if you have any questions. And if you have any questions, then... Oh, I see there are no more questions, actually. Cool. So I guess that's it for today. I hope you at least know how to not fall into any of the obvious traps when benchmarking, again, being the timer resolution, which is incorrect, not running the operation enough times for the measurement to be somewhat representable, or like just not remembering about the dead code, which can be optimized out, or running a lot of background noise, which might influence your results. So if you keep that in mind, you should be safe with benchmarking. Okay, so I guess that's it for today. I see there are no questions, therefore let me check out the chat in that case. Could one show what is the statistical amount of tests required by proving a null hypothesis? The rebel supervisor asks. I would have to look what's... Sorry, I'm not super familiar with statistical terms, so I'm not sure is the answer. I'm sorry, I don't know. Is it in general better to benchmark on faster machines? Okay, this is actually an excellent question. Ideally, benchmark stuff on the machines which you are intended to use for running the code. That's basically the best answer. As in, for example, if you are able to benchmark in production on real code, real examples, like for example, some samples of the incoming traffic, you can benchmark it, do that. Because that will be the best, most representable result you can get. Everything else is basically benchmarking on, like in lab conditions almost, where the real world has a nasty tendency of actually not being lab conditions. So yeah. Ideas for security bachelor's theses? Not really, because that really depends on what parts of security you're interested in. Like, jump on our Discord actually and tell us a little bit about what you're interested in, what areas of security you're interested in, and maybe somebody on the channel will have some idea, basically. But yeah, in the end is like I guess if you're writing a bachelor thesis, you should have at least some ideas, right, for it. So maybe you have some ideas, maybe you want to just discuss them. But yeah, I guess that's it. I don't see any other questions. So thank you for coming here, and I hope you at least learned something today. I know it wasn't as exciting as, you know, like typical hacking live streams, which sometimes are exciting. Sometimes. I'm not really sure about the next week's topic, but we'll think about something. Do keep in mind that there is this page out thing, so if you would like to write an article for us or help us in another way, then do check out the pagedout.institute page. And I would also like to thank my crew, especially Foxtrot Charlie, for being here today and helping me with the live streams. And I wish you all a happy evening, happy hacking, and happy programming. Have fun. See you next week or tomorrow if you speak Polish. And I'm going to leave you with some music.